Lecture 16, Architecture. The architect Philip Johnson collaborated with Jean Bergy to create the College of Architecture building at the University of Houston. The colonnade on the top does announce the idea of architecture, yet it serves no purposeful function. The building is directly reminiscent of Claude Nicolas Ledoux' design for the House of Education, which is a never constructed building that Ledoux had planned for a utopian community. Jean Bergy's design Johnson and Bergy's design reflects the contemporary stylistic trend called postmodernism, with its eclectic combination of multiple styles, past and present. You see this building with the colonnade and kind of building on top of it there. Well, the building on top doesn't do anything, it has no actual function. What it does aesthetically is it introduces the idea that this is a school of architecture. So you would see it on the campus at University of Houston, and you would say, oh, you mean the building with the colonnade on top of it? That must be the School of Architecture. It was based on, or at least borrowed from, this drawing of a building by Ledoux, which was never built, which was going to be the House of Education. This is an architect's plans, but never fabricated. This is an interior of the University of Houston's School of Architecture. We saw the outside with the colonnade on top. This lecture will examine the many facets of our built environment, its evolution from Greek temples and the Anasazi cliff dwellings to skyscrapers and postmodern designs. The look of our buildings and communities depend on two different factors: the landscape characteristics of the local site, which we call the topography, that's the landscape characteristics of the site, the topography, and the forms of our built environment as determined by the available technology, the forms of technology. Both are factors that affect the way in which we build structures around us. So again, you've got topography, and technology. Topography is the characteristics of the land, and technology is the materials and the skill available to build things on that land. And both of those things, the topography and the technology, are important to examine as we discuss architecture. Let's start with topography. Before we get to topography, here's our architecture study guide. Here's the terms we'll be looking at in this lecture on the built environment, on architecture. You can rewind as needed to access the spelling and whatnot. We'll also refer to this same study guide as the last slide, the last image in this lecture. So again, first, topography. A building's form might echo its environment, or it might contrast with that environment, and many early examples of architecture were indebted to resemble natural forms. The pyramids at Giza, which we see here, are thought to be deliberately mimicking the rays of the sun. You see the tiny people standing around and in front of these gigantic pyramids in Africa. Well, in Egypt. Well, those giant pyramids and the way they kind of come from one central point down to this tiny, tiny human at the base of them, because again, these pyramids were almost 500 feet tall, so this enormous height would perhaps mimic the rays of the sun coming from above, and many people believe that the pyramids were deliberately intended to mimic the rays of the sun above. Many Egyptian religions and sub gods and deities were thought to be sun gods. Some of the sun gods being the most important. Here's a Sumerian ziggurat. The Sumerian people believed that their gods resided in the mountains, and thus their ziggurats served as artificial homes for the gods. The Sumerian ziggurats that we see here were thought to be patterned after the mountains and the surrounding foothills, that the kind of man-made mountains. The Sumerians felt that their gods resided in the mountains, so when they built temples to their gods, they built kind of man-made mountains. Again, There were mountains in the foothills of their society, so they're mimicking the topography. They're mimicking the world around them. Topography means the land you live on. The Anasazi cliff dwellings in Mesa Verde National Park in southwest Colorado reflect a similar relationship between humans and nature. The caves provided a natural security that allowed the Anasazi to survive for hundreds of years. The kiva was a round room covered with stacked logs, which in turn created a type of dome up to an access hole. The roofs were paved over with stone to create a flat communal area. Down below in the kiva floor was a sipapu, which was a small round hole symbolic of the Anasazi creation myth, which described their ancestors as having emerged from the depths of the earth. What you see here is this fascinating architectural cluster of buildings and houses in the mountain and the cliffs of the of of in western the cliffs of western Colorado, where this civilization lived between 12 and 1300 BC. Um, and you see these ladders, these little wooden ladders, popping up out of these little squares in the ground. Well, this is this kiva and this kind of room below. I'll cut to the next slide, and you'll see a cross-section drawing of how these kiva structures existed. So don't forget the little squares where the ladders are popping up out of the floor, because we're going to now cut to a drawing which will show us a kind of a diagram of what's below those ladders and those square holes. Here's the ladder as it goes down from that square hole, and you can see there was this kind of subterranean kind of dome, kind of a basement, if you will, where they could store grain and supply and stay when it was cold or whatnot for safety and other room to live in. The Anasazi people had a myth about birth and creation, and this kiva hole and this coming up through the hole like being born was part of their culture. And this again is a civilization that lived for a very, very long time, hundreds of years, in these complicated cave-like cliff caves, kind of these caves along the cliffs of a very dynamic, interesting place in the American Southwest. Anyway, we're trying to talk about topography and how the Egyptians and the Sumerians responded to their environment, and here how the Anasazi people also responded to their environment, to the topography. We'll return when we talk about Frank Lloyd Wright to topography later on, but now let's move to technology. While the cliff dwellings are a response to topography of the place, the structure of the kiva roof represents a technological innovation for the Anasazi people. The basic technological challenges faced in architecture is to build walls and put a roof over the space that they enclose, because essentially architecture is building shelter for humans. And there are two basic approaches to building walls with a roof. Those two basic approaches are the shell system, and the shell system is one which basic materials provide the structural support and the outside covering of the building. So the walls hold up, in the shell system, like a seashell, the walls hold up the roof. That's one of the two basic approaches to building. The other system is a skeleton and skin system, which consists of an interior frame or skeleton which supports an outer covering, or a skin. And we're going to talk about the shell system and the skeleton and skin system and how they've evolved over the years. In buildings several stories tall, the walls or frame of the lower floors must bear the weight of the upper floors. So again, in the shell, in the skeleton and skin system versus the shell system, you've got different problems, which we're going to discuss as we move through our discussion of architecture today and the technology of architecture. But again, in buildings that are several stories tall, the walls or frame of the lower floors must bear the weight of the upper floors. So the ability of a given material to support weight is thus a factor in how high a building can be. Also, The horizontal span between elements or supports, such as walls or columns, is determined by a material's tensile strength. Tensile strength is real important in architecture. Almost all technological advances in architecture have either been made through the discovery of a new means of distributing weight or new materials which improved tensile strength. And we're going to talk about that as we move along. Um, Tensile strength is, well, we'll talk about that as we get to post and lintel construction. So first, load-bearing construction. The simplest method of building is to make the walls bear the weight of the roof, and this can be done by stacking bricks or stones up to the height of the roof. The kiva, which we saw a moment ago, was an example of a load-bearing construction. So, first we'll talk about post and lintel construction. The walls surrounding the Lion's Gate at Mycenae were load-bearing, but the gate itself represents a basic construction device called the post and lintel, a horizontal beam supported at each end by a vertical post or wall. So like post, you can think of fence posts. Fence posts are just vertical posts in the ground. And then a lintel is a horizontal element that kind of goes across the two. Lintel is the horizontal bit that goes across the top. So you can't have a building without a post and lintel because you have to have a doorway to get in and out. So there's a post, two posts and a lintel here. We call it post and lintel, even though it's posts and lintel. There's more than one post always. You can't balance a lintel on one post. You need more than one or two posts. So the Lion's Gate at Mycenae is the classic example of post and lintel construction. Post and lintel construction is fundamental to Greek architecture. Greek architecture, post and lintel construction again. In the basilica at Paestum, the columns or posts supporting the structure were spaced relatively close to each other to compensate for the stone's tendency to crack and buckle across long spans. Each column in the basilica is made up of several sections called barrels, which were grooved or fluted, which visually unites these sections to become one kind of long column. Each column also tapers dramatically towards the top and slightly towards the bottom, which creates a kind of bulge called enthesis. Enthesis deceives the eye and makes the column look vertical when you're far away from it. So the kind of bulging of these columns is an illusion that the Greeks put into their designs. The values of the Greek city-state were embodied in its temples. The temples were usually on an elevated site called an acropolis. Acro meaning above and polis meaning city, so above the city. The outer portion of the temple was a row of columns called a colonnade. A row of columns is called a colonnade, which supports the weight of the roof. The vertical design or elevation of a Greek temple is composed of three basic elements: the platform, the column, and the entablature. The relationship between these three elements is referred to as an order. A row of columns is a colonnade. This is the three Greek orders of columns. You've got the Doric, which is kind of plain, the Ionic, which is slightly ornamental, and the Corinthian, which is very, very decorative. The temple reflects a preoccupation with order, and in fact, so specific were the Greeks about the order of their architecture that there were three distinct classifications of the orders of columns: the Doric, Ionic, and Corinthian. The Greeks rarely used the Corinthian order, but it became a favorite in the Romans, who adapted just about everything that the Greeks ever invented. The Doric style is quite heavy in appearance compared to the Ionic. In ancient times, Doric was considered masculine, while the Ionic was thought to be more feminine. The temple to the Athena Nike is the oldest Ionic temple on the Acropolis in Athens. Let me show you a picture of that. So again, here's the three different orders: Doric, Ionic, and Corinthian, and you can see cornice, frieze, entablature, etc. All the different kind of elements that make the three classical orders of Greek columns. Egyptians had their own order of columns, but this is the classic Greek order of columns. Here's the temple to Athena, the Athena Nike. And many of you wear Nike shoes, and if you wonder where it came from, well, this is exactly where it came from. On the Acropolis in Athens, Greece, still standing, is this tiny and very beautiful temple of Athena Nike, and this is a great temple in the Ionic style. We see a colonnade, four Ionic columns with their capitals holding up the front of this temple. In the old days, back 3,000 years ago, Greek priests would hold ceremonies inside. Um, Actually, only in these very small temples, the ceremony and sacrifices would happen on the steps of the temple, and only the priests would be able to enter them to do certain rituals. The geometric order of the Greek temple suggests a conscious concern on the part of the Greeks to understand nature. They were really into understanding nature and everything about it. We spoke about that with the Fibonacci number series and the golden section, and the Parthenon is just right behind this building. You can't see it here. If we were facing this building, it would be behind us on the Acropolis, and it's of course the gigantic temple to Athena. Anyway, post and lintel construction. Here we have the ionic columns, which are the posts, and then the stone horizontals, which serve as the lintels. They are the stone elements that span the two. So again, so far we've talked about load-bearing construction. We went from the post lintel and the Lion's Gate at Mycenae to a couple of Greek temples and their columns and the orders of columns and more post and lintel. The problem with post and lintel is you can't span too far. If you look at the distance between those columns, they're pretty close together. They may be maybe 5 or 6 feet apart. You can't get a stone between them because if the stone was any. You can't get a longer stone between columns because the stone doesn't have very good tensile strength and it would crack. It would push down and crack. So they're kind of close together, and that gives you a kind of a crowded sense of space. Technology comes to change that. That technology is the arch. The arch is essentially the post and lintel with a little bit of evolution. You can see in the arch that you have no horizontal lintel. You essentially have two posts that start at the bottom and then they come up and they kind of gracefully curve towards one another and they meet in the middle. So it's kind of two posts that meet together. The lintel has been kind of absorbed into the design. And this is the arch. The arch is a really great invention and a really big deal. We saw again moments ago post and lintel construction and how they work, but now we need to see the development of the arch. The arch can span greater distances because gravity wants to pull that arch down, but it's preloaded and built in the opposite direction, so it's pushing upwards while gravity pulls down. So gravity actually makes the arch, the stone arch, stronger. It kind of holds it in place. So it's a really wonderful and very, very important invention. Here's the Pont du Gard aqueduct, which is in the south of France, and it is the most amazing thing that I'd ever seen. It's it's actually a waterway that the ancient Romans used to move water from the mountains to the city below, and it travels some 30 or 40 miles, and it moves water from one place to another, and all this is possible because of these beautiful arches, these very strong and beautiful arches, which allow water to be moved from one place to another. It's also a highway that cars can drive over, and it's still standing, although it was built 2,000 years ago. I was there a couple of Easters ago on holiday with my family, and it is the most breathtaking thing. And to think that an ancient civilization made it with no electricity or modern technology, and that not only does it still stand, but people still drive over it is just quite a testament to the ancient Romans' technology and to the strength of building with the arch. So, this is the arch. It's very powerful, right? It does great things. It can span far greater distances with stone than the post and lintel. Now, if you take a bunch of arches and if you stack them behind one another, you get a vault. You get a barrel vault. At top now you see an image, an illustration, a diagram of a barrel vault. A barrel vault is essentially a bunch of arches that have been kind of built behind one another. That's the top image of a barrel vault. Below it we see a groin vault or a groined vault. And a groined vault is simply two barrel vaults that intersect at 90-degree angles. And the barrel vault's real important because you have all the strength of the arch and all the open space of a vault, but you have more room for light to come in, which is important, of course, in a world where electricity hasn't been invented. Also, you don't want to use more stone material than you need to. Everything we've seen so far is made of cut stone, which is a real pain in the neck. You have to cut each stone, by hand, importing an incredible amount of labor and organization. Back to Rome. Here's the famous Roman Colosseum from an aerial view. It's on the edge of the Roman Forum. It's called the Colosseum, believe it or not because it is colossal, but it's called the Colosseum because there was a colossal statue of Nero outside of it, which is no longer there. But there was some gigantic 70-foot statue to the Emperor Nero outside it called the Colossus. It fell down when Nero burned Rome. But this was called, I think it's the Amphitheater to Flavin is the actual name of it. But it was a theater, an arena built, made very famous in the film The Gladiator, and I think there was an interesting chase scene in it in a recent film called Time Jumpers or something. Some recent adventure film I saw that they for the first time in 20 or 30 years they let them film a movie in the Colosseum. Anyway, earthquakes have destroyed it. It used to have damaged it. It used to have this outer ring would travel all the way around the entire stadium, and this is an enormous stadium. It was built again 2,000 years ago, but it was the largest stadium in the world for 2,000 years until the Yale Bowl was built in New Haven, Connecticut, one of the first big football stadiums. It would hold capacity crowds, they say, of over 50,000 people. Of course, we have larger stadiums now, like our Superdome in New Orleans, but again, this is built 2,000 years ago. And believe it or not, it had a engineered feat where it could have a canopied roof to keep the rain out. They used to flood this thing to have naval battles, mock naval battles with little flat-bottom boats. They'd have an underground system of elevators to bring up entertainment for animals and for gladiators to do various things. There is a myth that Christians were killed in the Colosseum. That is not true. That myth was created on purpose by Catholic priests because once the rumor and myth became believed that Christians were sacrificed in the Colosseum, then it became sacred ground, and it was not allowed to be destroyed. So very wisely and strategically, during the birth of Catholicism and organized Christianity in Rome, the priests and the early organizers of the religion, the priests, bishops, and cardinals, made up this idea that Christians were sacrificed at the Colosseum, and then it made the Colosseum sacred ground, and they started putting crucifixes on it and made it kind of a shrine, an altar to these imaginary dead people. And again, many people did die there, but it was never about killing Christians. Anyway, this plan of saying Christians were killed there was an excellent plan because it kind of assured of the Colosseum's longevity. The Colosseum's broken because there have been many earthquakes in Rome in the last 2,000 years, and also because, believe it or not, over the 2,000 years, people, not recently, but people in the past, 1,000 years ago, 500 years ago, would come and they would, after the Roman Empire fell, they would come and they would steal metal fittings that held the stones together, and they would recycle them to do whatever they wanted. This led to neglect, and the building was just ignored and neglected for hundreds and hundreds of years. In fact, from the end of the Roman Empire until the Renaissance, this was the whole Roman Forum, which you see behind the Colosseum here. The whole Roman Forum was just pastures for sheep to graze on. Anyway, the University of New Orleans has a summer program in Rome where I've taught the last 4 summers. I didn't go this summer. I went the last 4 summers before this year. And I had an apartment not 2 blocks from the Colosseum where we met and taught this very class, art appreciation, also a drawing class, a Renaissance history class, and Italian language. So if any of you are ever interested in taking University of New Orleans study abroad program, we have a pretty exciting and cool 1-month program where we spend the month of July in Rome. It's exciting. It'll change your life. It's not cheap, but UNO, as you all know, is not particularly expensive school, so you could spend more through other places. might consider the UNO Rome program. Anyway, back to the curriculum. Um, the Colosseum is built with lots and lots of barrel vaults. This image shows us an aerial view of all the arches and vaults that make the overall construction. Let me cut to the next slide. The next slide shows us um, a, a view from walking around the Colosseum, where you see that it's made of arches, and long curved vaults all around, and it's just this enormous stone structure that has withstood the test of time, 2,000 years, several earthquakes, and is still going strong. So, the Roman system of vaulting was in use throughout Europe for 1,000 years after the building of the Colosseum, and it was especially prevalent in Romanesque architecture, which used many Roman architectural conventions. The barrel vault over the nave of Saint Sernin in Toulouse, France, is a magnificent example of the Romanesque influence and the Romanesque engineering feat of construction. This is an interior view of the Pantheon. The Pantheon is an enormous domed structure. When you think Pantheon, you think dome. The Pantheon has a gigantic dome inside it. I think it's a 600-foot diameter, and this is the most enormous and amazing space. It was built by it was designed allegedly by Hadrian, a very important Roman ruler and emperor, who believed in advancing architectural accomplishments. Of particular interest was this building, the Pantheon, is the first to use cement. Now, what does that mean? Well, before they perfected the recipe for cement, all stone buildings were made of solid cut stones, big pieces of limestone and marble that were quarried and cut and placed together very carefully. This is an enormous building with gigantic interior space, with no posts holding up this huge dome. And Hadrian is credited with inventing cement or mortar, brick mortar, because once you have cement or mortar, then you can use little bits of stone to make a larger wall, and you no longer need to have this enormous labor pool cutting separate stones, but now rather you can cut just the front stones, the back stones carefully, and fill the insides with rubble, with kind of just rocks and mortar, kind of cement in a faster manner. The walls for the Pantheon are 12 feet deep at the base of the dome, and as they curve up towards the top, they taper to 6 feet deep, 6 feet thick. The top hole is called an oculus. So if you look up at the top of that, if you look up at the top of this photograph, you see this gigantic circle, the oculus, where light comes in. Well, the wall is 6 feet thick up there at the top of that. And then as the wall comes down, it gets wider and wider to 12 feet, and in some places 20 feet thick. Again, the Roman Pantheon consists of this enormous dome, which is set on a cylindrical wall, and extremely thick at the base, where it springs off to this taper above. The name of that window, the hole in the top of the dome, is called an oculus. It's where light comes in. If I can briefly describe how a dome stands up, a dome stands up because a dome is an arch that has been rotated kind of on its center point. So if you put a pin and balance the dome on a pin, if you balance an arch on a pin and then rotated it, that would be a dome. So a dome is a very, very strong structure. The Pantheon is a remarkable dome. It was built 2,000 years ago, and then for whatever reason, when the Roman Empire collapsed, they lost the magic recipe for dome building, and no dome this size was built successfully until Michelangelo helped design and engineer St. Peter's Cathedral 2,000 years, 1,600 years later. So it's kind of a big deal that this dome exists. If you ever get to Rome, this is a very amazing place. The two kings, Victor Emanuele and his son are buried. The early kings of Italy are buried there. Um, Raphael, the famous Renaissance artist, is buried there. This is a really important structure, slap dab in the middle of downtown Rome, ancient Rome. Here's a slide of an image of the exterior of the Pantheon, where you see an Egyptian obelisk and a fountain in front of it, and then the kind of colonnade and pediment of the building. Um, the dome is in the background of the whole space. Ancient Rome was originally a lot lower. So this 2,000-year-old building in modern Rome, where you see automobiles parked around it, seems very low and set into the ground. But that's because 2,000 years earlier, all of these roads were very, very low. In the ancient world, you would have stepped up a row of steps to get to this processional entryway. The modern world has changed that to avoid flooding and whatnot as a city has evolved. But here we see the gigantic dome of the Pantheon in the background, with its facade in the front that you would enter into, with these gigantic granite monolithic columns. Um, Whenever you think of the Pantheon, always say dome. Dome is the most amazing thing about the Pantheon, this amazing engineered dome that uses cement for its thick, thick 20-foot walls at the base, which taper to 6 feet at the top before the oculus above. When you see the Pantheon, you think dome. When you see the aqueducts at Pointe du Gard, you think arch. When you see the Colosseum, you should think barrel vault. When you see the Lion's Gate at Mycenae, you should think post and lintel. Those are kind of the fundamental architectural achievements of each of these structures. We're jumping back to Romanesque now, and we see the interior view of the nave of Saint Sernin in Toulouse, France. So Romanesque arches with this long vault, and some columns where arches spring off them, and it's pretty amazing, pretty beautiful. You've got this soaring high ceiling with all this masonry all around you. The next slide will show us a footprint of a blueprint, a floor plan of the building. Here's the footprint, the floor plan, what it looks like from above for the Saint Sernin Cathedral. And what's hopefully obvious to you all is a cathedral is a very important church, right? And this one is shaped like most cathedrals are. It's shaped like a crucifix. Not only is it shaped like a crucifix, but if you were to impose the body of Christ over this architectural plan, his head would go in the tabernacle, where the most important part of the Mass is held, where the communion is stored in the tabernacle. And then, of course, the arms leaving the heart right in the center, the altar, where the priest gives his Mass. And then the congregation would sit in the body of Christ. So the overall design for a cathedral is based on the most important image in all of Catholicism, the crucifix, which is the whole idea of Christ dying for our sins and resurrection. The fact that Christ dies and is born again and becomes the Savior of mankind. Well, that's the story of Catholicism. But that story of Catholicism becomes part of the design of the architecture for Catholicism. So when you build a Catholic cathedral, you put that crucifix into the very floor plan that it exists. We saw the Romanesque arch. Here's an example of a pointed arch, and this is called a Gothic arch. Gothic arches, through a bit of engineering, the Gothic arch can span greater distances and get even higher up. Here's a wonderful example of a Gothic pointed arch, which again can be even wider, span greater distances in this beautiful Gothic cathedral. The Gothic or pointed arch. Again, the advantage is it spans greater distances than the Roman arch. The most famous of all Gothic cathedrals is the Cathedral of Notre Dame in Paris. It is a Gothic cathedral, and in order to so the Gothic cathedral has lots of pointed arches in it, but in order to aid in the spiritual goal of this beautiful Gothic cathedral, it was the intentions of the builders to fill the walls with stained glass full of the narratives of the Old and New Testament to a mostly illiterate congregation below so they could see the life and times of Christ and the apostles, but also to fill the room with this colored light, like James Turrell's sculpture spoke about in the last lecture, to give it this kind of ethereal, kind of a spiritual kind of glow. So to fill a masonry building, a stone building, to fill a stone building with colored light, you need to fill your walls with glass. Well, glass is very beautiful, but glass is not very strong. You can't stack bricks on top of glass. So this Gothic cathedral with its Gothic arches and this high pointed situation, how do we make it so that you could have walls made of glass? Well, what the Gothic architects and the builders of the Cathedral of Notre Dame discovered was this wonderful term called the flying buttress. And the flying buttress is literally a small tower on the side of a building that has kind of a half an arch that leans in like a helping hand, like an arm, and literally holds the wall up or takes some of the weight off the wall. So the Cathedral of Notre Dame is full of these flying buttresses, these kind of external supports and towers. I'll cut to the next image, which shows the diagram of that. Here's a side view of a flying buttress. Flying buttress is this tower that leans in and holds the building up. And there's dozens and dozens of these around the Cathedral of Notre Dame, and they're very very symmetrical and very beautiful and very ornate. And they add to the overall Gothic style. But their purpose was to allow the building to have these enormous stained glass windows in them. When you fill walls with stained glass, you remove the inherent strength of the wall. So the trade-off between having all that natural light coming through those colored glass and creating that wonderful meditative and spiritual glow inside the cathedral was that you needed to create some kind of exterior bracing to hold the walls up. And these are called flying buttresses. So when you see Notre Dame, you've got stained glass windows to consider, you've got Gothic arches, and in this case you've got the flying buttress. So up until then we've talked about pretty much everything was made out of stone. Stone with some brick and mortar cement, but really stone. And stone for a couple thousand years ruled the built environment. The technology was stone and perfecting stone. Wood was still used for some horizontal beams on some of those huge Greek temples. They would use gigantic wooden beams to span across the tops of some of them. But for the most part, it was all about stone. Well, in the 19th century, cast iron construction becomes possible, and architecture is determined by the innovations of technology. Well, stone was there for so long, and then finally during the 19th century, iron, which had been known about for centuries, but was not really readily available until the beginning of the Industrial Revolution, through the invention of the steam engine and other mining technologies and other technologies that let iron and then eventually steel become available. Anyway, this is the entranceway to the Paris Metro, which is made out of cast iron. It's not so important that the metro station is made out of cast iron, the entranceway. What's important is that you can't build an underground subway without the advent of iron beams. You need I-beams and angle iron and other beams to hold up the ground beneath you. It would have been impractical to cut these tunnels without the use of iron and steel. So iron becomes the paramount material. The artist here, Hector Gumar, has the sense to use this iron, this brand new early 20th century material, to introduce the metro train station, but it's iron which allows for the beams to hold up the Paris subway system. Here is a very famous structure. I call it a building. I suppose it's more of a tower. The Eiffel Tower, and it's made by Gustave Eiffel. He designed and oversaw the construction of this enormous tower. It's over 1,000 feet tall. The Eiffel Tower was built for the Paris Exposition in 1889, and it soared to 1,000 feet, instantly becoming the tallest structure in the world. And the openness of the tower's lattice construction allowed the wind to pass through it, making it extremely resilient to the forces of nature. Believe it or not, many Parisians initially hated the look of this great monument, and some newspaper articles argued that it was a complete waste of time and money. But it soon became clear that it heralded in a new potential for the architectural construction, and this is the beginning of the skeleton and skin system, which we're going to talk about. Um, Up until this building is built, the Eiffel Tower, pretty much everything we've seen was the shell system. Pretty much everything we've seen has been walls that hold up the roof. Well, once steel and iron are invented, and the big innovation for the Eiffel Tower is the introduction of iron and iron lattice construction. Um, but once we've got I-beams that can be used to hold up a building, then the walls no longer need to hold up the ceiling. The beams alone can hold them up. So the term skeleton and skin system refers to the fact that a skeleton of let's call them bones or beams can hold up the roof, and the walls can be no longer load bearing. So the Eiffel Tower is all about the innovational technology here is the use of iron and lattice beam construction, cast iron and lattice beam construction. We're going to jump back to a more humbler building technology before we jump forward to a more complicated technology, and that is frame construction. Again, the importance of steel and iron in architecture are very important, and we'll get to those in a moment. But two humbler technological innovations also added much to the look of our built environment. Those two are standardized milling specifications for lumber, namely making 2x4s, which led to uniform construction methods and the advent of balloon-framed housing. The first introduction of the 2x4 was in Chicago in 1933, and balloon frame housing is still common today. Most of our houses more or less look like this illustration, even though it's been around for 50, 60 years. Actually 70, 80 years. Um, in balloon frame construction, a framework or skeleton of 2x4s are nailed together, windows are placed in the skeleton, and basic post lintel construction go from there. The entire skeleton is sheathed with clapboard or planks or some other suitable material. The roof is more complex, but not unlike the new truss system that was used for the basilica of the old St. Peter's Cathedral. Let me show you this next slide. Here's a drawing for the old St. Peter's Basilica in Rome, and you can see that this triangular truss system for the roofs has been around for a long time. The truss is a triangular framework that is one of the strongest forms in architecture. The triangle is very, very rigid and strong form, and it spans longer distances than a single wooden beam. We've all been in New Orleans during the rebuilding in a post-Katrina world, and you'll see building companies show up with these pre-made triangles for the trusses, and they'll just kind of stack them up and nail them together really quickly. They're very, very strong structures. Before the 1920s and 30s, when you wanted to build a house, you went to a sawmill by yourself, and you ordered the lumber you wished to build your home, and you'd say like so many 3x8s or so many 6x6s or so many whatever you wanted. Home Depot and lumber yards didn't have standardized uniform building methods until the 1930s. We go to Home Depot now or Lowe's or a lumber yard and we get our pre-made lumber. But before that, you had to go to a sawmill where they made the lumber from trees and order exactly what you wanted. And different builders had different preferences. That's why a lot of the really old houses in New Orleans have gigantic timbers behind the walls, which are more than strong enough for the construction. Modern construction tries to deal with an economy of materials and a premium of insulation and energy conservation. We're trying to make houses less expensive to build now because raw materials are so hard to find. 100 and 200 years ago, there were lots more trees around, so some houses have some massive timbers inside of them. Anyway, the truss system is part of balloon frame housing, which is what makes most of our houses stand up. It was used in St. Peter's Basilica because the triangle is such a strong shape. Here's the triangular truss, and once you put that inverted triangle into it, it can span greater distances. You'll see these again at construction sites when they're building houses in our new Orleans. and they're very strong and very inexpensive to make. Um, Again, an example of a modern house built with again, we're talking about a lot of fanciful architecture and a lot of great innovations with the arch and the dome and the post-lintel construction, balloon frame construction, two by fours, and this building, which might look like either your house or a house in your community, is important to see as well. Okay, so again, this is an example of a bungalow style construction, and more or less the modern 2 by 4 balloon framed house. Our New Orleans homes look a bit different, but more or less you get the point. Back to steel and reinforced concrete construction, and we've left the kind of ordinary domestic situation, which is far more important than these magnificent buildings. When you speak about architecture, what percentage of buildings in the world are these fanciful domes and aqueducts? Not too many. They're important art historically, but perhaps the home you're listening to this lecture in right now is more important. There are more regular people living in regular houses than there are people living in these magnificent structures. Nonetheless, let's talk some more about the evolution of architecture. When C.R. Ashby, a representative of the British National Trust, visited the United States in 1900, he was especially impressed with the architecture he saw in Chicago. He recognized that an aesthetic handling he recognized that quote an aesthetic handling of material had evolved out of the industrial system, end quote. While a young architect named Frank Lloyd Wright impressed Ashby the most, his mentor, Louis Sullivan, was perhaps most responsible for Ashby's response. The Chicago fire of 1870 had provided architects with the unique opportunity of rebuilding the entire core of the city. As Sullivan saw it, the problem facing the modern architect was how the building would transcend the sinister urban conditions from which it must arise. He sought an architecture which was lighter than the heavy appearance of buildings such as the one we see here by Henry Hobson Richardson Marshall. This is this big, gigantic, heavy building, and this is the kind of thing that people like Louis Sullivan and then later Henry Frank Lloyd Wright were responding against. Um, the answer, uh, Louis Sullivan felt, rested in the development of steel construction techniques combined with a system of ornamentation. A steel skeletal frame freed the walls of load-bearing necessity, opening it to ornaments and a large number of windows. The vertical emphasis became fundamental, and the building no longer seemed massive. So let me explain what's wrong with this building. The Marshall Field Wholesale Store in Chicago is a massive building. It's one, two, three, four, five. It's 7 or 8 stories tall, and it's massive. And if you look at those lower floors, the lower floors have to hold up the upper floors. So the lower floors are very, very thick and very, very massive with kind of smallish windows, and then as it goes up, the floors above are held by the floors below it. So this is an example of the um, shell system where the walls hold up the roof. So so the walls hold up each floor, and the walls hold up um, the whole building, the floors above it. Now, if they could free these buildings, which seem very heavy and kind of like a big prison, this building looks like it weighs billions of pounds and it just sits there hugging the earth. It's really oppressive and heavy and closed. But if they could find a construction technique, in this case steel, which could allow them to go to a skeletal frame, then the walls would no longer be load bearing. The walls wouldn't have to be so thick and heavy. And that comes with the advent of the I beam, steel. Um, this is a building by Louis Sullivan called the Bayard Building in New York, and it's an example of again, it has internal I beams, so these walls full of windows are now freed to have more glass in them. So this is a kind of a big evolution. Also, Louis Sullivan adds this kind of floral decoration on the buildings. Um, he's famous for his Louis Sullivan is famous for his phrase "form must follow function," um, and he's trying to. He's working at the time when Henry Ford's designing the Model T Ford, and he's dealing with kind of a practical, industrious way of building buildings here. So again, for Sullivan, the primary function of a building was to elevate the spirit of those who worked in it. He felt that the slide we saw before this of the Marshall Field wholesale store was not a very good place to work and a good place to be. It would be kind of a heavy downer. Um, Frank Lloyd Wright was a student of Louis Sullivan, and he made this house called a Roby House for a family in Chicago. Uh, you can see the cantilevered porch in the left side of this photograph of the house. Frank Lloyd Wright tried not to make houses that were on the land, but rather Frank Lloyd Wright, the famous architect, tried to make houses that were of the land. He tried to include the topography along with his technology. You can see here that the cantilevered roof is an extension of the roof of the house, so that when you're inside the house or outside the house, there's really no difference. The roof line doesn't change. It's all kind of there in this exciting way. Your textbook does another wonderful little works in progress section, and it highlights Frank Lloyd Wright, the American architect and one of the fathers of modern architecture in our country, and his 1935 design for what is arguably the most famous modern house in the world. It's Edgar Kaufman's Falling Water House. You see here a kind of concept drawing. Frank Lloyd Wright was asked to build a house near a waterfall, and he didn't just build one near a waterfall, but rather he built one right over the waterfall that kind of, with this cantilevering of concrete, felt as if it were felt as if it were waterfall itself. Again, Frank Lloyd Wright doesn't build houses on the land; he builds houses of the land. Um, the Kaufman family contracted Wright in 1934 to make this project. The initial drawings didn't appear until the following September, but Wright felt that the architect should first conceive of a building and have it in mind before he begins to make the sketches. The first drawings, one of which we see here, were done in 2 hours when Kaufman made a surprise call and said he would like to see the plans. Wright completed several floor plans in that session. As an exterior view from across the stream, we see a remarkable similarity to the finished house. Kaufman, who was skeptical of Wright's radical design, hired engineers who said that the 18-foot cantilever wouldn't function structurally. The contractors ultimately added twice as much steel as Wright called for, and as a result, the main cantilever droops to this day. Frank Lloyd Wright made the house in the same spirit as his famous Prairie House, which we just saw a moment ago, which again were of the land, and the forms of the Falling Water House deliberately blend in with the environment. Here's the finished house. We just saw the preparatory drawing, and they're very, very similar, as you can see. Here's an in-progress section when they were scaffolding the house up to pour the cement forms and whatnot. So, let me get back to this skeleton and skin idea, because we've introduced it, but I don't think it's really made evident until we look at these next few images. Here's Le Corbusier's drawings for the Domino House project. And here you can see exactly what I mean when I say skeleton and skin system. The 6 beams, the 6 rectangular solids, which hold these 3 cement slabs apart, well, those 6 beams, those are the skeleton which hold the building together. So now, through the use of reinforced concrete and through steel beams, you can make a house where the interior walls can go anywhere you want, or you can have no walls at all. Now you can make a house where the walls can be made out of anything you want. The walls don't hold the house up anymore. Skeleton and skin means like the bones in your body, like your own skeleton, it means that the bones, in this case the six beams, hold the building up. So you're free to put your partition walls wherever you like, or have no partition walls at all. And this is a big thing for the built environment. It allows the artist to really change their ideas. Here's Le Corbusier's house, the Villa Savoy, and again, now you have this huge open space below where you can drive in. So again, now that we have the skeleton and skin system as opposed to the shell system, now you've got all this colonnade of steel beams covered in cement here around the building, and you've got this open, breezy entranceway where the whole building is sitting up on these little sticks. Now this would not have been possible in the shell system where the walls had to hold up what was above it. Um, Again, here we have the 1928-1929 building by Miles van der Rohe, and you can see it has the whole front wall of the building is made of glass now because the wall doesn't hold the roof up. That's done by some very small, discrete steel beams. So the advent of steel and the I-beam and then reinforced concrete allow for these skeleton and skin buildings to exist. Also, this new style of architecture, this very clean and elegant style with very little ornamentation, became known as the international style of architecture, especially after this German pavilion was built in 1929. That's when the phrase was first coined. Um, our next slide shows us a floor plan of this building. Here's a floor plan of the building, and you see, as the floor plan suggests, that it's very simplified and minimal. Um, an open space of architecture with bands of marble, sheets of glass, and stainless steel poles. The entire structure seems to shimmer in the light. Um, this simplified design and this elegant and clean sense of design with little ornamentation again is referred to as the international style. Um, Miles van der Rohe made this piece, which is literally a house. You've heard the expression, people who live in glass houses shouldn't throw stones. Well, Miles van der Rohe actually built a glass house because the glass walls don't hold the roof up. That's held up by the thicker white steel beams, the I-beams, which have been painted white so they don't rust. And now you've got a glass house. This would not have been possible in the shell system where walls held the house up, but rather is possible in the skeleton and skin system because the steel beams hold the roof up. Miles van der Rohe and Philip Johnson collaborated to build the Seagram's building in New York City, and this is considered the first modern skyscraper. Um, if you look down at the lower floors, they're probably 20 or 25 feet tall, but that level down below is open so you can enter the building and not feel like you're in that oppressive situation that we saw earlier in that building in Chicago made out of stone. Here we have modern materials, steel and glass, and we have the skeleton and skin system where the whole building just shimmers in glass, and this is allowed to happen because the walls don't hold up the building, but rather the steel beams, the skeleton within. Philip Johnson made this place called literally the Glass House. Again, similar design to the Miles van der Rohe, but again, only made possible because of this change in technology, the invention of the I-beam, the mass producibility of steel, and reinforced concrete. I mentioned reinforced concrete. Reinforced concrete does not have to be just flat shapes. Ario Saarinen's architectural work rejects the international style, which we've just seen, all that kind of very geometric stuff. And it seeks its unity in design through the observation of natural forms. Here's the famous TWA terminal at Kennedy Airport in New York, and it was designed so that the building's interior space would be in contrast to the openness of the broad expanses of windows and the sculptural mass of the reinforced concrete roof and walls. So again, the tremendous exterior concrete wing seems to resemble the very notion of flight itself. The wing uh, effect is also restated in the designs of other airports that Saarinen designed around the same time. But again, you look at this building, and it looks like it's an airport because it seems to introduce, through its very design, the idea of flying. It looks like a bird's wing. It looks like a spaceship. This is the idea that the building introduces its subject. This is an airport terminal built in 1962, and it's still standing. It's in fact it's actually the JetBlue terminal in New York City, and this is made through reinforced concrete. Those complicated forms that we see there are made of concrete with rebar inside them. Um, Concrete has great compression strength, and steel has great tensile strength. So together, you get a great combination of materials. And when you build these complicated warped surfaces, you get this wonderful organic structure, which we see here in this TWA terminal. If I showed you a slide of this for an exam or quiz, and I said, what would be the principal architectural innovation for this image, I'd expect you to say reinforced concrete. So we talked about contrapposto a couple of lectures ago with architecture and with Greek and then Roman figuration that seemed to twist uh, and get that S curve in the spine. Well, here's a building by Santiago Calatrava, which does just that. It's the most fascinating building, which seems to go well beyond the buildings from the 1960s and 70s in America, 50s, 60s, and 70s. Now in the 21st century, we've got this beautiful and really unexpected building, which it literally twists. The building twists as it soars up 54 stories, and it consists of these 9 cubes, which each twist a total of 90 degrees from top to bottom. So the whole building just kind of turns as it goes up, mimicking the twisting bottle, which we see in the next slide in the drawing. So again, this is, a concept drawing by the architect, and then a moment ago we saw the actual building. A fascinating building made now possible through um, reinforced concrete, through the skeleton and skin system, and also now through such complicated computer modeling software, which allows us to consider space and make the blueprints for this extremely complicated building. Um, Rem Koolhaas is an architect who teaches at, I think, at Harvard University, and he's been involved in all kinds of building projects, which again utilize these modern building materials and this modern technology. Here's another wonderful building in Barcelona, built on or about the time of the last time Barcelona hosted the Olympics. Um, that gives the city a lot of attention. And it's 31 stories high, and it's this kind of bullet-shaped building, the centerpiece of a new commercial district planned by the city, and it's made of reinforced concrete crowned by a glass and steel dome. It's a fascinating building and really seems to introduce a kind of new idea of architecture as it breaks away from that international style and begins to, I don't know what to call this, kind of this new 21st century style of architecture where forms become far more complicated. Richard Meyer was never too happy with the kind of impersonal community life of those skyscrapers, like the Seagram's building and the other great skyscrapers in Chicago and New York. So he kind of made this building, which deals with a more in-depth way of moving the habitants of the building to and from one another and to their purposes. So it's a real effort to get kind of a harmony between building and function and nature. Architecture is a complicated job, and it's not simply about making egocentric towers and monuments. You have to really take into consideration the users of the building and the people who are going to be in the building and what the function of the building is going to be. And that really brings up the next topic, which is infrastructure, community life. Here's Central Park, an aerial view. Um, New York City looking north. I showed this slide, I think, in the very first chapter. I pulled it from chapter 16 then, and I showed it to you when I showed you Christo's gates. and how he filled this park for just a couple of weeks with those beautiful orange gates outlining the pathways of this wonderful park. I told you at the time that the park wasn't there naturally, and that all kinds of soil was carted in, and the lakes were created with digging machines and explosives, and hundreds of trees were planted, and all kinds of exciting things happened to build a park. Well, Frederick Law Olmsted and Calvert Vaux actually designed and had the park constructed. That's a big deal as we start to deal with community life, infrastructure. So again, the Seagram's building is a stunning example of the international style of architecture, but it also represents an impersonality and an anonymity of urban life. Um, it's important for artists to try to figure out a way to architects and artists to include a better quality of life for the inhabitants of the buildings. Central Park was just that. Central Park was actually built to let New Yorkers feel like they could retreat from the urban sprawl to a more natural and relaxing and graceful atmosphere. So Olmsted and Vaux designed a park with graceful curves and generous spaces, intentionally getting the absence of sharp corners outside of the park, and they wanted to suggest and imply leisure when they built and designed this park. Um, so here's Central Park. I think I have a slide of Christo. Yes, here's a repeat from Chapter 1 as we wind down on the Chapter 16. But here's Christo's Gates in Central Park, just to remind us how far we've come since our first discussion weeks ago. But the greatest accomplishment, perhaps, for Vaux and Olmsted was their plans for um, the community of Riverside in Chicago. And that is, Vaux and Olmsted envisioned and laid out the plans for the first suburb. Um, they wanted to design a place. They laid out the general plans for the city of Riverside, which is the first suburb of Chicago. The design for Riverside set the standard for suburban development in America. The pace of that development was slow until the 1920s, when suburbia suddenly exploded, and by the 1950s, the suburbs were growing at a rate of 10 times that of cities. For the first time, cities began to lose population. And that was a really big deal. Um, New Orleans has been around as a city for hundreds of years, but the West Bank and Covington and the North Shore and Jefferson Parish, those were not really of any population consequence until the invention of the suburb. And the suburb requires you to have a highway system. You can't have a suburb unless you can get people back and forth to where they work. So again, as we talk about infrastructure, you've got the Los Angeles Freeway Exchange. You know, Los Angeles is all about car culture. I mean, New Orleans is too. We have some pretty cool highways and exit ramps all over our city. But infrastructure, it's a really big deal. Um, the two great consequences of suburban immigration were, first, the rise of the automobile as the primary means of transportation, and second, the collapse of the financial base of the urban center itself. In 1930, the city of Los Angeles decided not to spend any more money on mass transit, but instead began to build a giant freeway system. In 1940, the Pennsylvania Turnpike and the Pasadena Freeway both opened, and America is really a highway nation. We have, without a doubt, the greatest highways of any country in the world. We are an automobile nation. So, that's the story of infrastructure, but let's jump back to the Renaissance quickly. And now we see Leonardo da Vinci, who made these drawings in his notebooks in 1503, where he envisioned cutting a canal. In the city of Florence, which would have given it access to the sea, and the same way that Voxted and Olmsted and Vaux, I'm sorry, built the first suburb, and then the highways came to bring people back and forth so they could work in the city and live in not the country, but the suburb, kind of below urban, not quite rural, not quite urban, suburban, kind of in the middle. Was happening as even Da Vinci was considering urban planning and infrastructure. We saw the Pointe du Gard aqueduct in the south of France, the ancient Roman way of bringing water to people. You got to have water. You can't have a city without infrastructure. We saw the Paris Metro as an example of infrastructure. And again, historically, when infrastructure collapses, cities begin to deteriorate. You don't have to tell us about that in New Orleans, where we experienced the collapse of our infrastructure with the levee system. So, um, let's look at some more. This is a strange little story. A woman named Muriel Euclides is a self-appointed artist in residence at the Great Kills landfill in Staten Island, New York, and she is a non-salaried artist in residence, that is real interested in garbage. Um, the Great Kills landfill is the largest garbage dump in the world. They say it's visible from outer space. I hope that's not true. But anyway, um, Muriel Euclides, the artist, has been in this revitalization project for the last I don't know 20 or 30 years, it seems, dealing with the conflict between the fact that she's an artist, but also a wife and a mother. And she felt that, quote, I'm a wife, I'm a mother, I do a hell of a lot of washing, cleaning, cooking, renewing, supporting, preserving, etc. And now I will simply do these maintenance things and flush them up to the consciousness and exhibit them as art. So again, she makes art on and about waste and all that we throw away. This is an aerial view of the Great Kills landfill in Staten Island, this enormous garbage dump, which is pretty awful. But again, New York City is so big, they got to put their garbage somewhere. And now we're going to conclude this chapter 16 on architecture, by having a look at urban planning and renewal. Here we see the Statue of Liberty, which everyone's aware of, and then in the background we see Lower Manhattan, where the Twin Towers and the World Trade Center once stood. The World Trade Center were actually 7 buildings, 2 of them being World Trade Center 1 and World Trade Center 2, the two very tall towers, which were hit by terrorist airplanes on September 11, 2001. At the end of that day, all 7 World Trade Center buildings were destroyed or collapsed. There's been a big revival project to put new buildings there, and Daniel Liebenskind is the architect who was selected to build what they're calling the Freedom Tower, and designing the whole kind of complex of buildings down at what's called Ground Zero. It's just, again, important to understand the evolution of architecture and how we've come in the built environment from the shell system with simple post and lintel construction onto the skeleton and skin system, which allows us to have glass walls and cast concrete, reinforced concrete floors. Here's the final image in this chapter, where, well, actually we have one more. That's the this is the proposed new World Trade Center complex, World Trade Center plan, which will include the Freedom Tower, and it's been modified many times, unfortunately, by city planners and other agencies that have been involved, including the Homeland Security Department, because they don't want it to be so easily vulnerable to another terrorist attack. And here's the final plan for the cultural center at the site of the World Trade Center, where we see again exciting possibilities in what can happen as these buildings, I wouldn't say are rebuilt, but as new buildings come to replace those buildings. As we conclude chapter 16 on architecture, I've posted the terms for brief review. So again, as we conclude chapter 16 on architecture, I've got the list here to go over, make sure I've covered all these terms. Certainly, typography means the land you're building on. Technology means the technology you bring to the building. Ziggurats were something that the Sumerians used. Kiva were those in the Colorado cliffs. The shell system and skeleton and skin system we've talked about at great length. Tensile strength is, again, how far you can span a post, a lintel between 2 posts. Load bearing means just that, how much weight you can put on something. The post or lintel, we saw the Lion's Gate at Mycenae. The arch, we saw the Pointe du Gard aqueduct. The posted lintel, again, would be the lion gate at Mycenae is a great example of that. The lintel is the distance you can span between posts. The lintel is burdened by its tensile strength. The arch is comes out of the evolution of the posted lintel, and the arch is essentially two posts that curve to each other until they meet at a keystone, and the arch overcomes the limitations of tensile strength in stone, in a stone lintel especially. The dome gives you an even greater open space, and the dome is essentially an arch that's been rotated on its z-axis. The arch would be a great image of the arch would be the Pointe du Gard aqueduct. The dome, we saw the Pantheon, which also introduces the use of cement. The barrel vault is a series of arches behind one another. The groin vault is two barrel vaults that pierce one another. The pointed arch is used in a Gothic cathedral, where we also saw the flying buttress in the Cathedral of Notre Dame. The flying buttress is kind of a tower with an arm that reaches in and helps the Gothic cathedral full of stained glass windows to stay upright. If you didn't have flying buttresses, the walls would crumble with all that weight pressed on those stained glass windows. Greek columns, we spoke about the order of Greek columns with Doric, Ionic, and Corinthian orders. The colonnade, the elevation, the platform, the column, and the tablature are all displayed on the diagram of the order of Greek columns. You can look at those there. Cast iron is a big deal as cast iron comes in as a new technology and changes the built environment. We see that most evidently in the Eiffel Tower. Wood frame construction and the truss are pretty humble, but they're how most of our houses are built. Wood frame, balloon frame construction, 2x4 construction, and the triangular truss system, which helps us span greater distances because of how strong the triangle is as a building material. Cast iron leads eventually to the mass production of steel, which is a high carbon form of iron, and the steel I-beam, which lead to again the skeleton and skin system. Reinforced concrete we saw in that wonderful Cheetah building. The kind of warped surfaces. Cantilever was the kind of patios in Frank Lloyd Wright's Prairie House as well as his Falling Water House. The international style is again used with glass and steel and limited, no ornamentation and clean lines, and we see that in the Seagram's building and modern skyscrapers. Postmodernism would have to do with architecture. We spoke about that with the Jean-Michel Basquiat painting chapters and lectures ago, but postmodernism has to do when architecture ignores form and function. All of the earlier parts of architecture were all about embracing form and function, but early on, the first slide today, we saw the architecture school at the University of Houston, and it had a colonnade on the roof. Well, that colonnade served no purpose. It was just there to introduce the building. So that'd be an example of postmodern design. And then finally, infrastructure, where we spoke about Volksted and Olmsted and Vaux, where they had designed Central Park, and then they'd invented suburbs, and how we saw highway systems, and we saw the Pointe du Gard aqueduct bringing water in, and the Paris Metro. That's all infrastructure. You can't have a city without infrastructure. So that concludes lecture 16 on architecture. There is a quiz for this lecture, which is either posted or will be soon posted on the Blackboard server. Thank you.